Okay, so let us apply all the concepts that we have into some problems that you'll come across. Okay, the first one is you've been given a loop, you've been given a track, and there is a loop part to the track, okay, with some radius r, and we want to ask from what minimum height should we release this mass such that it will complete this loop. Okay, so problem is actually straightforward once you understand what's going on. Okay, we're going to use two concepts here. First concept is we need to figure out the minimum condition for it to complete the loop. Okay, and then the second concept is going to be, hey, how do we find the height once we know the speed at this location? We need to find the speed here first. If we know the speed here, then using the speed we can figure out the height here. Now we're assuming, of course, that the object is being released at rest at this height. Okay, so the question is, with what speed should it be, from what height should it be released so that it completes the loop? So first part in the problem is, part one is figure out v, and then the second part is then to figure out h. So you need to know that how to do this. Okay, so now in order to figure out v, we're going to go back to the condition. What is the condition for the object to complete the loop? And the condition is very simple: the fact that the contact force at this point has to be equal to 0. So that's a minimum condition. Okay, the contact force at the top has to be equal to 0. So if we were to draw a free body diagram for this object, we would have the force mg going down, Fn going down, and the result of mv square over r pointing in this direction. Okay, and now that we have all this information, we can rewrite mg plus Fn equals mv square over r. Now my minimum condition, as you've guessed correctly, minimum condition, okay, is that Fn be equal to 0. Okay, which means that mg equals mv square over r, and this says that v equal to square root of g times r. So now that we have the minimum condition, we can simply use conservation of mechanical energy to figure out the height from which it must be released. Okay, now in the beginning, since the object is at rest, it has 0 kinetic energy. Its potential energy is simply the gravitational potential energy, nothing else, mg times h. Its final kinetic energy, now when it is at the top of the loop here, the final kinetic, it's moving with speed v that we just found, and if you see, and this is where you have to be careful, it is at a height of 2r from the bottom. So just make sure that you keep that in mind. So it is equal to 1/2 m times v, which we found to be square root of gr square, plus we have m times g times 2 times r. Great, we have our equation. Let's simplify this. We have mgh equals 1/2 mgr plus 2 mgr, and if you see, half plus 2 is nothing but 5/2, so this gives us 5/2 mgr, and so h, what happened? So h is equal to nothing but 5/2 times r. So this is the minimum height from which it must be released. Now of course we are assuming that there is no friction and all that, but in that case the minimum height with which you must release this object at rest so that it completes the loop is going to be 5/2 r.